welcome to the deep dive. We are really excited to have you here with us today for this one.
Yeah, absolutely. Thanks for joining us.
So I want you to imagine something. Imagine pushing a massive update to, like, 1 million users across the globe, right?
The classic nightmare scenario.
Exactly. You flip the switch, and within 30 seconds, your monitoring dashboards just light up red. There is a fatal bug in the code.
Oh, man. I mean, in a traditional setup, you are scrambling at that point.
Right. Your entire company is offline, and, you're losing revenue by the second.
It is terrifying.
But if your DNS architecture is set up correctly, you just execute a single command, you shift the traffic back to the stable version, and honestly, nobody even notices the hiccup.
And that right there, I mean, that is the difference between treating your domain name system as just a static phone book and, well, utilizing it as an active, highly intelligent routing engine.
Yeah.
The days of a simple, flat mapping of a human-readable domain name to a machine-readable IP address those days are completely over in modern enterprise architecture.
They really are. And that is exactly what we are focusing on today. We have a very focused stack of architectural notes and exam prep materials covering AWS Route 53's core functions.
Specifically, it's 7 distinct routing policies.
Right, and the critical traps you need to watch out for. Because whether you are prepping for the AWS Solutions Architect Associate exam, the SAA-C03, or you just want to understand how global internet traffic actually works, our mission today is very clear.
We want to transform you.
Exactly. We're going to transform you from a casual cloud user into an architect who understands exactly how to direct global internet traffic using Route 53. Okay, let's unpack this.
Let's do it.
What makes Route 53 so fundamentally different? To me, it feels less like a directory and more like, I don't know, an ultra-smart traffic cop standing at the center of the internet.
I like that.
Like one with deep architectural awareness of how the whole city is functioning, not just the one intersection.
That analogy holds up really well, actually, especially when you consider that a standard DNS service acts like a bad traffic cop.
Right.
A bad cop just blindly points cars down a road because, well, that's what the sign says. They are completely unaware that a bridge is out 5 miles ahead.
Yeah, they're just following the paper instructions.
Exactly. But Route 53 operates at the intersection of availability and user experience. It controls the entire flow and resilience of your application.
So it's looking at the bigger picture.
Always. Yeah. You could have the most beautifully designed, hyperscaled compute resources in the entire world, but, I mean, they are totally useless if your users are routed across the globe, resulting in massive delays.
Or routed to a server that is already crashed, which is even worse.
Right. Route 53 is basically the frontline defense for your entire AWS environment.
Right, because if the dispatcher sends the ambulance to the wrong hospital, it really doesn't matter how good the doctors are at that hospital.
Exactly. The system has failed.
So to control this massive amount of traffic effectively, an architect needs strict rules. And AWS gives us 7 foundational routing policies. Let's start with the first 3.
Simple, weighted, and multi-value routing.
Right. Now, I have to push back conceptually here on the very premise of using DNS for this kind of heavy lifting.
Oh, okay.
Yeah, because if we have a policy called simple routing, which, just hands out an IP address, why push traffic distribution logic up to the DNS layer with weighted or multi-value?
I see where you're going.
I mean, shouldn't a dedicated elastic load balancer handle that kind of traffic distribution? Relying on DNS for that feels almost like trying to steer a ship by mailing instructions to the passengers.
That is a great point. And you are hitting on a very real architectural debate here. It really comes down to the difference between regional bottlenecks and global scale.
Okay, break that down for me.
Well, an elastic load balancer is fantastic, right?
Yeah.
But it is typically regional. It exists in one specific geographic area.
Right, like US East or whatever.
Exactly.
Yeah.
But Route 53 operates globally. If you want to distribute traffic across entirely different continents, or say between an on-premises data center and the cloud, you just cannot rely on a single regional load balancer.
Oh, because the traffic hasn't even reached your region yet.
Precisely. You have to make the routing decision at the DNS level before the user's request even enters your physical network.
Okay, that makes a lot of sense. You are catching the traffic while it's still out on the wider internet.
Exactly.
But if simple routing just blindly hands over whatever IP address is on file, how does weighted routing actually function in the real world? Especially when you factor in DNS caching.
That is the crucial mechanic to understand. So let's say you are executing a canary release. You're rolling out a new version of your application.
Right, slow rollout.
Yeah. You want 90% of your traffic to hit the old stable servers and just 10% to hit the new experimental servers.
To limit the blast radius if something goes wrong.
Exactly. With weighted routing, you literally assign a weight of 90 to the old infrastructure and 10 to the new.
Okay.
So when a DNS resolver queries Route 53, Route 53 acts almost like a loaded die. It calculates the probability based on those weights and hands back the corresponding IP address.
But wait because of time to live or TTL. That resolver might cache the answer, right?
Yes, it will.
So it's not a perfect 90 to 10 split on a per user basis?
Correct. It is a probabilistic distribution of DNS queries. It's not a strict load balancer for individual HTTP requests.
Ah, I see.
But at scale, across millions of requests, it averages out perfectly to that 90 to 10 split. It allows you to test new features in production with a tiny blast radius.
Okay, so that covers weighted. What about multi-value routing? I see in the documentation that it can return up to 8 IP addresses at once.
Yes, it can.
Why throw a list of IPs at a user's browser instead of just giving them the best one?
Well, multi-value routing is essentially a form of client-side load balancing, but with a really critical layer of intelligence added.
What kind of intelligence?
Instead of just blindly handing out 8 random IPs, multi-value routing strictly integrates with Route 53 health checks. It constantly monitors your resources.
Oh, so it knows what's alive.
Right. If one of your web servers crashes, Route 53 dynamically removes that server's IP from the list it hands out.
So it basically guarantees that the list of options the user receives only contains servers that are actually awake and functioning.
Precisely. And if the user's browser tries the first IP on the list and it happens to fail for, I don't know, some transient network reason.
Like a random timeout.
Exactly. The browser can instantly try the second IP on the list without having to make another full DNS query.
Oh, wow. So that drastically improves the perceived reliability of the application for the end user.
It really does. It's incredibly resilient.
Okay, so simple is for basic single server setups. Weighted gives you proportional control for safe deployments. And multi-value gives the client a resilient, pre-vetted list of healthy options.
You got it.
But weighted routing is completely blind to the user, right? I mean, it treats a user in Tokyo and a user in New York exactly the same.
It does. It has no idea where they are.
So when a global architecture requires actual physical geographic awareness, we have to look at the next 3 policies, right? Geolocation, geoproximity, and latency routing.
Yeah. This is where we transition from just distributing load to actively shaping the user experience based on the physical map and network topology.
I love this concept because it always reminds me of ordering delivery food.
Oh, yeah.
Yeah. When you open up an app to get dinner, you have a distinct choice to make. Do you want the restaurant that is physically, geographically closest to your house, like the place right down the street?
Right.
Or do you want the restaurant that can navigate city traffic, hop on the highway, and deliver the food the absolute fastest right now, completely, regardless of the physical distance?
If we connect this to the bigger picture, that analogy perfectly captures the architectural distinction between these policies,
Yeah.
particularly when we scale it up to enterprise cloud applications. Let's look at geolocation first. Geolocation routing makes decisions based strictly on the user's physical borders. Are they querying from the UK? Are they in California? Are they in Japan? You use this when you must adhere to physical lines on a map.
But in an internet context, why do physical borders even matter? Shouldn't a cloud architect just care about delivering the data as fast as humanly possible?
Well, in a perfect world, yes. But in reality, compliance, data sovereignty, and licensing dictate architecture.
Oh, the legal stuff.
Exactly. Think about a global streaming service. If they have the rights to broadcast a movie in France but not in Germany, they cannot simply route a German user to the French server just because it's fast.
Where they get sued.
Yep. So geolocation routing guarantees that mapping. You draw a hard digital border. If the query originates from a French IP address, they go to the French server. If not, they are blocked or routed elsewhere.
It's literally a digital bouncer checking IDs at the door.
That's a great way to put it.
So how does geoproximity differ from that? Because, I mean, geoproximity sounds like it also cares about geography.
It does, but geoproximity introduces the concept of a dynamic border through a mechanism called bias.
Bias.
Yeah. With geoproximity, Route 53 looks at the geographic location of your users and the geographic location of your AWS resources and routes the user to the closest resource.
Okay.
But by applying a numerical bias, an architect can artificially expand or shrink the geographic footprint of a specific region.
Wait, okay, so going back to the delivery food analogy,
Yeah, let's hear it.
it's like artificially expanding the delivery zone of one specific restaurant on the app just because you know their kitchen has extra staff tonight and can handle a massive surge in orders.
While the closer restaurant is overwhelmed.
Right. So you shift the zone.
That is exactly how it functions. Imagine you have servers in US East and US West.
Okay.
Suddenly, the East Coast wakes up and your US East region is just getting hammered with traffic. By increasing the bias on your US West region, Route 53 essentially moves the invisible geographic dividing line further east. Now, users in Chicago who would normally route to the East Coast because they are physically closer are seamlessly shifted to the West Coast to balance the load.
That is incredible. You are dynamically rewriting the physical map of the internet to shed load.
It's very powerful.
But what about the users who just want their data delivered as fast as possible? Borders be damned.
Well, that requires latency routing. Latency routing completely ignores state lines, country borders, and geographic proximity.
Just totally ignores them.
Completely. Its singular goal is optimizing network speed. And the mechanism behind this is brilliant.
I've always wondered about the mechanics here. How does Route 53 know what the latency is for a user who hasn't even connected yet?
It's a good question.
I mean, it's not pinging every single user's laptop in real time, right? That seems impossible.
No, doing that would introduce way more latency than it solves. Instead, AWS utilizes its massive global network of edge locations.
Oh, like the ones at Power CloudFront.
The exact same infrastructure. These edge locations are constantly measuring the network latency, or round-trip time, between themselves and the various AWS regions.
So they have a map of the network speed.
Yes. AWS compiles this massive, ever-updating database of network topology.
Okay.
So when a user in London queries your website, Route 53 looks up their subnet, checks the latency database, and realizes that even though the Paris region is physically closer to them, a fiber optic cable is congested today, so the US East region will actually respond 20 milliseconds faster.
Wow, so physical distance really does not equal network speed.
Not on the internet.
Latency routing dynamically reacts to the reality of the internet's weather patterns, like congestion, BGP routing anomalies, fiber cuts,
Yes.
and routes based on pure performance.
Exactly. It maps the internet as it exists right now, not as it looks on a physical globe.
That makes so much sense. But, whether you are routing for speed or for compliance or for load distribution, none of it matters if you are routing traffic to a dead server.
That is the ultimate truth.
Geographic awareness has to be paired with state awareness. Which brings us to the final routing policy, failover routing and the deeper mechanics of Route 53 health checks.
Yes, this is the absolute bedrock of high availability.
Right.
Failover routing allows you to create a robust, active-passive architecture. You have a primary resource handling 100% of your traffic, and a passive secondary resource, perhaps a static maintenance page hosted on S3, just waiting on standby.
Okay, so a backup plan.
Exactly. Route 53 routes everything to the primary, but only as long as it is healthy.
Here's my question about the mechanics of that, though.
Sure.
If the system is constantly checking a pulse, how exactly does failover routing know when to pull the plug without causing chaos?
What do you mean?
Well, you don't want your entire global traffic failing over to a static page just because a health checker experienced like a 1-second network blip, right? How does it avoid false positives?
I see. It avoids them through global consensus and configurable thresholds.
Global consensus.
Yes. Health checks are not just a single script pinging your server from one location in a basement somewhere.
Right.
AWS deploys a whole fleet of health checkers distributed in regions all over the world. These checkers constantly send requests to your endpoint.
And what are they looking for? Just a ping?
They can check a specific web page, look for a 200 OK HTTP status code, or even search the page for a specific string of text.
Oh, so it's not just checking if the server is powered on, it's actively verifying that the application is returning the correct data.
Yes. And to avoid the split brain scenario you mentioned, where one checker has a network blip and triggers a massive failover, the system relies on a quorum.
A quorum, so they have to agree.
Exactly. By default, a certain number of these global checkers must agree that your endpoint is actually down.
That's smart.
Furthermore, you as the architect define the failure threshold. You can dictate that an endpoint must fail 3 consecutive checks, spaced 10 seconds apart from multiple global locations, before Route 53 officially changes the state to unhealthy.
So it's a highly rigorous verification process. It basically demands a consensus before making a drastic architectural shift.
It has to be. And the moment that unhealthy threshold is breached, failover routing instantly kicks in.
Boom. Traffic move.
Yep. It stops returning the primary IP address and seamlessly starts returning the secondary IP.
And then what happens when the main server comes back online?
Once the primary server recovers and passes the health checks again, the system automatically heals itself and shifts traffic back.
Okay, so we've covered the mechanics behind the 7 policies. Simple, weighted, multi-value, geolocation, geoproximity, latency, and failover.
That's all 7.
Understanding how they function under the hood is critical for your architecture. But proving you know them on the SAA CO3 exam requires a slightly different skill set, doesn't it?
Oh, absolutely. The test makers are notorious for setting traps.
Here's where it gets really interesting, because on a multiple-choice exam, the phrases fastest response time and closest user sound suspiciously like the exact same concept to an untrained ear.
This raises an important question, and you have just identified the single most common trap that test takers fall into on the SAA CO3.
I knew it.
The exam will frequently present a scenario where an enterprise company wants to provide the best possible user experience for a global audience, demanding that their application loads as quickly as possible.
And the options will have both latency and geolocation.
Inevitably, they will both be sitting there in the multiple choice options.
And the immediate instinct is to deduce, well, if the server is physically closer geographically, the data has less distance to travel, so it will load faster. Therefore, geolocation is the answer.
That logical leap is exactly what the exam writers are preying on, and in the context of AWS definitions, it will absolutely cost you points.
Ouch.
You must separate these concepts strictly by their mechanical definitions. Latency routing is exclusively about network speed and performance.
Okay.
If an exam scenario uses keywords like fastest response time, lowest network latency, or optimizing performance, the answer is unequivocally latency routing.
Even if the prompt mentions that the user base is spread across, like, 50 different countries?
Yes. Do not let the mention of global users trick you into choosing geolocation.
Right, because geolocation is different.
Geolocation routing on the exam is strictly about the physical map and boundaries. The keywords for geolocation are entirely different.
Like what?
Think compliance, data sovereignty, localizing content, or restricting access to specific geographic regions. Geolocation does not care about speed, it cares about the law and the map.
It's a semantic trap, but it's totally grounded in real architectural differences.
Exactly.
To ensure you, the listener, are completely immune to these tricks, it's time to put this knowledge to the test. Let's run a quick testing, Grant.
Sounds fun.
I'm going to play the role of the test taker. I'll read out 3 distinct exam-style scenarios built directly from the concepts we've explored. Let's see if we can spot the patterns.
I'm ready.
Starting with Scenario 1. A financial institution has a critical web application hosted in the U.S. East 1 region. They have provisioned a disaster recovery site in the U.S. West 2 region. The architecture mandates an active-passive configuration to minimize costs. The core requirement is that traffic must automatically divert to the U.S. West 2 region only if the primary application in U.S. East 1 becomes completely unresponsive.
Okay, so look strictly at the architectural requirements here. You have disaster recovery, active-passive configuration, and the trigger automatically divert only if unresponsive.
Right.
The system must actively monitor the state of the primary application. This is the textbook definition of failover routing integrated with Route 53 health checks.
Because it demands state awareness before shifting traffic. Spot on. Okay, Scenario 2. Pay close attention to the phrasing here. A global gaming company is launching a highly anticipated multiplayer game. To provide a seamless, lag-free experience, the company requires that player traffic is dynamically directed to the AWS region that will provide the absolute fastest connection time regardless of where the player physically resides.
And this is the trap in action.
Yep.
The prompt mentions a global company and where the player physically resides, trying to bait you into a geographic policy.
Because it wants you to pick geolocation.
Exactly, but the core requirements are a lag-free experience and the absolute fastest connection time. Because the goal is purely network performance over physical proximity, the only correct answer is latency routing.
Perfect. It's ignoring the borders to optimize the speed. All right, final scenario, scenario 3.
Let's hear it.
A software development team is deploying a major UI overhaul to their e-commerce platform. To minimize the blast radius of potential bugs, the team wants to send exactly 5% of their live production traffic to the new UI, while keeping the remaining 95% of traffic safely on the stable legacy UI. They need to monitor the new UI for errors over a 24-hour period before gradually increasing the traffic load.
The defining constraints here are send exactly 5% of traffic and keeping the remaining 95%.
Right.
This describes a canary release pattern. The architect requires strict proportional control over how the DNS resolver hands out IP addresses.
So it's not based on health or speed.
No, it's just percentages. The only routing policy capable of executing this probabilistic split at the DNS layer is weighted routing. You simply assign a weight of 5 to the new infrastructure and 95 to the legacy stack.
That makes total sense. If you can spot those patterns, the state-aware active-passive triggers for failover, the strict network speed optimizations for latency, and the probabilistic percentage splits for weighteds, you're going to absolutely crush this section of the SAA CO3 exam.
Without a doubt.
So what does this all mean? When we zoom out and look at the whole picture, the core takeaway here is that Route 53 is not just a basic directory mapping names to numbers.
Not at all.
It is a comprehensive, highly intelligent traffic controller that dictates the resilience, the geographic compliance, and the ultimate speed of your entire AWS architecture.
It truly is the unsung hero of global cloud deployments. And, I want to leave you with a final thought to ponder today, something that really builds on the mechanics we've explored.
Oh, I like a good thought experiment. What is it?
Well, right now, Route 53 DNS routing can make incredible, complex decisions based on real-time global network latency and active quorum-based health checks, right?
Right, it's very reactive.
Exactly. It reacts powerfully to what is currently happening on the network. But what happens in the near future when these routing policies transition from reactive to entirely predictive?
Predictive.
Yeah. Imagine an architecture that utilizes machine learning to continuously analyze global internet weather patterns, BGP fluctuations, and historical traffic surges, and actually shifts your traffic away from a specific region before a catastrophic network failure even registers on a health check.
That is wild.
Yeah.
So the system wouldn't just be reacting to a broken bridge. It would predict that the bridge is going to fail tomorrow based on structural stress data and begin preemptively diverting global traffic today.
And doing it without dropping a single packet.
That is just wow.
That predictive agility is exactly where the next frontier of high-availability cloud architecture is heading.
Well, until we get access to clairvoyant, time-traveling DNS, we will have to rely on mastering the deeply powerful mechanics of these 7 foundational policies.
Very true.
We hope this deep dive has helped you pull back the curtain and see the intersection of global cloud traffic for what it really is. Keep exploring, keep building, and if you are sitting for the SAA CO3 exam soon, trust your knowledge.
Look for the underlying mechanics and watch out for those semantic traps.
Okay.